All right, so thanks for coming to today's lecture. It's the second lecture in this subject. So can first of all, can everyone hear my voice and also see the shared screen? Now the screen is a slide with lecture one, a summary of lecture one. Is everything good? Is everything good?
Yes, we can
Oh,
hear.
that's great. Thank you. Thank you. Thank you very much. Okay, cool. So first of all, I think I'd like to talk a little bit about the lectures and tutorials in the following. The first thing is we have made the record of all the lectures and tutorials in the last semester, then which means you can watch on all the lecture records from the UTS Online. Then, which means coming to the lectures and the tutorials are not compulsory in this semester. And also because the videos are recorded already, then there's no meaning of redoing the lectures in this at this time during the class. So instead, for the lecture part, what we want to do is we require you to watch the video of each of the lecture before. Sorry, I'm getting students in before the class. All right, so have a watch on the video before the class. Then during the class, we are not redoing the lecture again, but instead, please bring your questions to the class. Then you can ask. So for example, when you watch the video and you find some parts are not that clear to me, clear to you, then you can ask questions during it. And what we want to do during the class is, first, I want to do some discussions and also the activities on the class. That's the first thing. And the second thing is, if something is quite important, I will introduce that again with you, but not in a complete lecture way. I'm going to introduce the very important part for each of the lecture, and then that you have a better understanding from both the recorded video and from the lecture as well. And also, if in the lecture there are other activities that we want to do, we will focus on that. Then after that, if you still have some questions, then we can discuss on those questions. So during the class, if you have some questions, you can post it to the chat, or we definitely have time to discuss the questions. Then if you want to do that, and during that time, you can just unmute yourself and ask. All right. And for the handout activities or for the tutorials, we have the full records on the UTS Online as well. Then, which means for the handout activities for the tutorials, we will do the similar things to what we did in the lecture. But during the time, you tutor, I mean, Marlene is there as well. You can ask questions, or Marlene can show you something else or some important things during that. But for today's lecture, for today's tutorial, Marlene will do a normal one because the record in the last semester is not that good on lecture 2. So he will redo a normal tutorial in today. And another thing is we are trying to, as I mentioned before, we're trying to bring some of the tutorials back to the lab, and then you can play with real sensors. We're still discussing about how to do it because a lot of limitations at the moment. So a very huge computer lab, now the capacity is not that enough for us. So we need to figure out how to do that, but we're definitely aiming for bring some of the tutorials back, maybe 1 or 2 days with 3 hours to play with real sensors. And also the for those kind of like real kind of activities or real tutorials, the safety is our priority. All right, so we try to make it safe. So we're still working on that, but we will definitely let you know a little bit later. And again, that real tutorial is not compulsory either. So which means you have your right to choose not to come. All right, but if you want to come, then you can play with real sensors. And things are still not confirmed, but we're aiming that. We are aiming to do that. So please wait for the emails from us. All right. Okay. So that's start of lecture today. In the last lecture, we mainly introduced about what I did and what's the research in our center, and also what is the mechatronic or robotic system looks like, right? Then we mainly introduced the teaching team and also some details about this subject and what we are going to run in this semester. All right, so in the handout activities, I think Marlene is with you with some kind of like a Linux, ROS, and also like some initial image processing things, and also play with the cameras. But mainly, we can't borrow cameras from the Mechatronics Studio, but you can play with that with your with the webcam on your laptop, right? And then the homework, and also so the homework and also the warm-ups for this lecture is there are some activities in lecture 1 then we want to discuss with, right? So in the lecture notes, I've shown a lot of videos. Let me know if there's this kind of videos in the on the UTS Online. Then we'll show it again. But I think I put videos on it. So there are some videos about the sensors control. Sorry, the sensor control used in mechatronics or robotic systems. And the first video is about the this robot soccer or robot football, and it's quite funny videos, right? And the other one is
time on the CPU
called the LSD SLAM. I think if you do know SLAM, what is SLAM? So SLAM means simultaneous localization and mapping. So that is mainly the eyes for the robot. Which means in SLAM, we need to use sensors to sensing the environment and to build a map of the unknown environment, and at the same time, use the map to locate itself. All right, then you can see that use the camera. You can use the camera to map the environment and also locate the camera itself. They can see the blue ones, they are the camera pose, and the green dots, they are the environment. They are the structure of the environment reconstructed when the camera moves. All right, so that's the second video example, and the third example is also SLAM. But SLAM is LSD SLAM is a semi-dense SLAM, and it's using stereo camera instead of using a single camera. They use the stereo camera, which is at the same time you can have two images from the two cameras, and then when we use that, you can see a much larger scale can be applied by using the proposed SLAM algorithm, right? So it's autonomous driving, like tone scale or something. Then when you drive, you can reconstruct the environment. Then it can locate the camera or locate the car itself, and you can see that's the reconstruction of the surrounding environment. All right, and it's a very large scale. It's the detailed view of that. So that's the example 3. So the difference between the example, example 2 and 3. One is using a single camera, and the other is using a stereo camera. All right, so then the example 4.
Just 21 adult camp, about 5. Who says Rome? Who says Rome was an adult camp nation? They're rebuilt.
You see that? So this is a very interesting title, right? So the paper is pretty good. The paper published in, I think, CVPR or ICCV some year. So that is the top conference in computer vision. And also the journal version is published in PAMI, which is the top journal in engineering. It's not only in computer vision, it's in engineering. And you can see people always said Roma is not built in a day, but they are trying to build Roma in one day, And this is there are some results. You can see they use the photos surrounding the environment, and try to use the photos to reconstruct the as you can see, you reconstruct the buildings in Roma, right? So that's the example 4. So for example 4, they're dealing with images as a single camera, but they are from different cameras, which means you have images from different viewing point and angle. Then you try to rebuild the buildings together with the textures and RGB. All right, so that's the example 4. And example 5 is from Georgia Tech, which is a very traditional visual studio.
So the challenge today.
So I'm not going to show the video again, because I suppose you've watched it already. So they use the camera. It's an RGB camera. It calls Space Ranger. So I'm going to talk about it a little bit later. They use the camera on the end effector of this industry robot. Then they want to use the information got from the camera to control the robot to pick up something, right? For example, if you have something in the environment and you don't know the location of that object with respect to the robot base, then it's quite hard to pick it up, right? But with the video serving, with the help from the video sensor, then it can do this kind of control. So that is video serving. And the other one is also the example 6 is also the video serving. It's also the video serving, but it is on the application of a medical case. So if you want to do the biopsy, you want to insert needle in the soft tissue. Then even you have a very good plan about the trajectory, but because the soft tissue it can deform, right? It's deformable soft tissues, then the trajectory may not be the same as what you planned, and it probably cannot reach the target location, right? And with the help of the sensing techniques, can do a feedback control, which can reach the targeted location, right? So those are the 6 examples I listed, and that's the discussion. We are not discussing in groups, but try to think about questions for each of the examples. So I make it in some groups because they are close to each other. The first one is the example 1, which is the robot soccer, and the second group is example 2 to 4, which is LSD slam and the stereo LSD slam and the building Roma in a day. And the group 3 are the 2 video serving ones, to remember. All right, so the questions are, first, what sensors are used in each of the example? Right, and the second question is what kind of things the system can achieve? And the second question is how it can be done. All right, so those are the questions. Please think about it in 1 or 2 minutes. I suppose you think about it already, and then feel free to unmute yourself to answer any of the questions with any of the examples. All right? Yeah, cool. All right, so can anyone answer the questions for any of the example? So feel free to unmute yourself and answer the questions. Don't worry, so feel free to talk about that. Can anyone answer the questions for any of the one of the example? All right, so let's go with examples one by one. So example 1, can anyone answer the questions, the following 3 questions on that? Try to answer that. All right, so that's let me try to answer that one by one by myself, and then feel free if you can answer the questions, and feel free to unmute yourself and try to talk and discuss with us, right? So for the example 1, that is the let's go back to that. That's the robot socket. Sorry about the sound. That's the robot socket. So it's quite interesting. So there are different levels of robot socket, and this level they use the robot they call now. That's a robot. I think it's from German company. And for that level of robot socket, they all use the same robots. Then they will program on the robot, and they will play with the socket. And again, this is not teleoperating. All right, it's not teleoperating. So everything will be on the robot itself. So which means we need to we need to program with a program with some algorithm or some control that to control the robot to play with the socket. But good thing is inside the robot there are some control already in it. For example, if the robot falls down, then there is a control to let the robot stand up. So for some basic control is done already, but you need to do some kind of like higher level control. For example, which direction the robot is shooting, right? So where is the ball? And if the ball is there, what we're going to do, what the robot is going to do, something like this. And it's quite interesting. At UTS, we used to have a team, but the team is not from our center; it's from the other center. One of my supervisor, he helped to supervise the team about the localization and mapping about SLAP part. All right. So first question: the sensor it used, the sensor that the robot used in this case. So normally we use some visual sensors to detect the environment and also detect the ball, right? So here on the robot, this it's a stereo camera. It's a stereo camera there. So they use stereo camera, definitely. It's not RGB, so it's a quite old version of the robot. At that time, we didn't have RGB sensors. So for this case, they use a stereo camera on the eye's location, if you can see. Then they use that sensor to locate the robot itself in the playground. All right, and what the features they use, if you can see, the ground is green and the some markers, some lines, they are in white. So it's quite easy to detect the lines. So what people always do in this case is they will detect the lines from the stereo camera, and then use those lines as the feature to do the localization of the robot. Which means from the eyes and to observe the lines on the ground, then it can by developing some algorithms, the robots can know where is it in the ground. All right, so that's about localization or navigation. And also they use the camera to detect the ball. And you can see the ball is in red and the ground is in green, right? So it's quite easy to detect the ball by using the color. All right, so they detect the ball as well by using the stereo camera on the head. But that is the main sensor it used for the higher level control of those robots. And another thing it used as well is the IMU, the initial measurement unit. I don't know if you heard of that. It's some kind of like combination of the gyroscope and also the accelerators, which can provide you the linear and angular acceleration and velocity at each time, but with some error and bias. But the good thing is we can use that to do some control and also even for the localization and navigation. For example, when the robot falls down, then the IMU can tell you where is the robot down and how you can control it back to the street, standing straight, right? And also the this IMU can provide you some kind of like relative poses along with the time with the error as well, then which can help the robot to do the navigation and localization itself. All right, so those are the two main sensors in this case, and I think I also introduced what the robot can do and also how it's done, right? But not in that details. So if you are interested in more details about how to control the robot, how to localize the robot, how to navigate the robot, then search on the website about SLAM problems. All right, the SLAM problem is the main problem for the autonomous robot in the unknown environment without teleoperating. All right, so that is for example 1 and example 2 and 3.
Application. Does DSLAM can use
Wait a minute. Yeah. So
over including many camera rotations and sequences with little structure.
So example 2, in example 2, it's a SLAM problem, but it uses semi-dense, as you can see from the bottom left figure. So they try to use the paths on the image with higher gradients as the features when they do the localization and also the mapping. So in the image, the higher gradient areas are always the edges. So that's why you can see that the features here detected always on the edges, and for most of the cases, the edges we can present the structure of the environment. Right, so this is what they propose. They call LSD SLAM, or semi-dense like mapping or localization or SLAM. And what sensor it used? They used the single camera. So in this case, it's a single camera. It's a single camera. And then they use a single camera, detect the features with higher gradient on the image, and they try to build the map of the environment and also at the same time calculate the 6-off pose of the camera itself. All right, so it is example 2. How to do that? That's a SLAM problem as well. Okay, so example 3. So the differences between example 2 and 3 is mainly about sensor. So here in this case, the sensor they used is a stereo camera instead of a single camera. A single camera we call it mono camera or monocle camera. So by using stereo camera instead of use monocle camera, let me ask you a question. So what's the differences? What's the difference? What's the main difference between a single camera and a stereo camera? What's the main difference? Think about that. Think about the question. Feel free to unmute yourself and ask a question. Sorry, answer the questions or talk. Think about that. So what's the differences between a single camera and a stereo camera? So it's quite obvious. One is a single camera, the other is 2 cameras, right? But what's the difference behind that? So what's the difference from using a single camera and from using 2 cameras together? Yes, I got a lot of very great answers on that. The difference is about the depth. That's 100% correct. So why is that? Why is that is, I'm going to introduce a little bit in this lecture, but following, I'll let you know how why it's about that, and also in the next lecture, I will show you the principles about stereo as well. All right, so for a single camera, you can't get. Sorry about using my hand. So suppose for a single camera, you can't directly get the depth of the feature from a single image. Why is that is, suppose here, this is your image. So for me, I am the camera center, right? So if you're thinking a ray from the camera center to a pixel on the image and make it longer to the 3D direction, right? So all the points along that ray will project it onto the same pixel of the image. And which means after you have a single image, then you have a pixel. You don't know what's the depth of that pixel because all the points along that tree will project it onto the same pixel. right? So which means from a single image from a single camera, you can't get the depth. But for stereo, it's a bit different. It's a bit different. When you have two cameras together, then you find that pixel is, so all the points on that pixel will be on that tree, right? Will be on that tree. Then you have a second camera. If you can find the same, the image point, which projected from the same object is there, then you will know the object will also on that ray. So which means you have two rays from two cameras. And then the intersection is the 3D point of that object projected onto the two cameras. And which means we can get the depth. We can get the 3D location, then which means we can get the depth of that object, right? So that is main difference comparing single camera to the stereo camera, right? And then we will definitely introduce the principle of a single camera and also the stereo camera in today's lecture and also in the next lecture. All right, then let's come back to to another question. If you come to the LSD SLAM
These are estimated
of the single camera. So suppose we can't get the depth from a single camera, right? But how can we do this reconstruction? Think about that. Think about this question and answer that to me. Right? So supposing we have stereo camera, then we know the depth, right? But even by using a single camera, we still can do this kind of reconstruction, which means we still can recover the depth, right? So how this can be done by using a single camera? Think about that, and give me your answer. Yeah, try to think about that. It's good questions, right? So it's quite interesting. It's some kind of like what kind of information we can get and what we can achieve based on those information, right? Yeah, those are, I think I got some questions, got some answer. Yes, I think I got a correct answer. All right, so normally what we think about here is we are not changing the lens. That's the thing. So if you change the lens, things get complicated. You will note it a bit later because we will introduce calibration as well. We will introduce the intrinsic parameters and the calibration. I'm talking about it a bit later. So which means if you have a camera, some intrinsic parameters, you can do the calibration and you can get the numbers prior to when you're using it, right? So in most of the cases, we do want to change the focal length. Want to have a fixed lens, then we can use it in the rest of the application, and we can calculate those things. We can calculate those intrinsic parameters before we apply it. All right, so the answer, I think we got it. I got a correct answer from the chat already. So suppose we have a single camera, and from one single view, we can't get the depth, right? But think about when the camera moves. When the camera moves, so when the camera moves from here to here, then you have an image from here, you have an image from there as well. And if they are overlaps between the two cameras, then which means it's some kind of like you use the motion to create a stereo, right? And then in this case, you can do triangulation and you can get depth. right? So which means if you have a single camera, then you move the camera. So if the camera is static, then you can't recover the depth. But when the camera moves from here to here, then you have two images from different viewing points. Then you can get the depth similar to what you have in the stereo, right? Right. So this is called structure from motion. Structure, which means the reconstructing of the environment, which means the depth from the motion of the camera. All right. So there are some limitations. There are some limitations on both the single camera structural motion, or we call the multiple view geometry, and also the stereo. So it's hard to say which one is better, but I'm going to explain it to you now about some kind of like the pros and cons for each of the setup. So for a single camera, the good thing is because all the images are from a single camera, then the setup of the sensors will be the same. Then it's quite easy to get the correspondences, which means feature matching, and it's quite easy to get the link, the tagging between the images. For example, if you want to do this triangulation, then you need to know the corresponding the matching to the image points, which presenting the same 3D object, right? So you need to do this kind of feature checking. So we will have a lecture about this kind of like feature checking later in this subject. And then you need to do this kind of like feature checking or feature matching. But from a same camera, it's quite easy to do that, right? So that's the good thing. And there are some bad things for that. One thing is, if the camera doesn't move, then you can't do anything. The camera must move. And if the camera moves quite fast or quite different from your previous image, then you definitely lose the overlap. Then you can't. I don't know why I always get students calling in the waiting room. All right, then if the camera moves quite fast, then you lose the overlap between them. Then you lose the checking. Then which means your system failed. Right. So that's the first bad thing. The second bad thing is you can't get. So you can get the triangulation and you can get the depth of the feature, but without any other information, then you can't get it in the real scale, in the real world scale. All right, so your camera moves here from here, you can do the triangulation, but you don't know exactly where what's the distance between the two cameras, between the two camera motions, right? And then which means it has a 3D, but it's up to a scale to the real world. So you can't get the real scale. In this case, it's the same. In this LSD mono camera case, it's the same. So you can reconstruct the environments, but it's up to a scale to the real world. All right. Then comparing to monocle camera for the stereo cameras, the good thing is you don't need to worry too much about the motion because I mean you still need the checking if you want to use them together. But from a single view, it always has a fixed camera relation or camera pose between the two cameras, right? And when the camera moves from here to here, you still get two views together. You still got two views together, and with a proper overlap between them. So which means you from a single view, you can always get the depth, right? So that's the first good thing comparing to the mono. The second good thing is about scale. As I mentioned before, so if a single camera moves here from here, you don't know exactly how long the camera moves, right? But if you have a prefixed two cameras as stereo, then you can always measure or calibrate the real distance between the two camera centers. So in this case, you know a scale already. You know a scale already. Then which means when you do this triangulation, you get the depth, and that depth is with the real scale. this has a very good thing in the application is when you use a single camera, then if without doing a loop closure, so I'm not talking too much about that, then when the camera moves, you can get a trajectory of the camera, you can get the 3D environment reconstructed up to a scale to the world. But because you can't get the real scale, then which means it's quite easy to get drift. So which means the longer the trajectory is, the more error you get from the result. But for the stereo camera, because you always have the real scale, then the drift comparing a single camera is much less. It's much less. This is my experience in a lot of research and projects. All right, but stereo camera is not perfect. Let's come back to the bad things. So the main bad thing for the stereo camera is you can't make a stereo camera with a quite large baseline. The baseline means the distance between the two camera centers. Why is that? Is the feature checking or the feature matching will affect a lot on the distance of the camera, on the viewing angles of the camera. All right, so which means if you have a longer baseline, then you will probably cannot get the matchings from the two or checkings from the two images. So I have experience when I did an ERC linkage project for the underground mining vehicle, like autonomous driving things. Then we tried to make a 1 meter stereo camera. We made by ourselves. So we made a stick and we put camera on that. It's roughly about a meter for the baseline. But the thing is, I can't get any feature matching between the two images. That's the problem. So we try to use some other methods to use to get some rough matching, and then we can do some calculation something. The question comes to why we want to make the baseline larger. Can anyone answer me the question? Why we want to make the baseline of the stereo camera larger? Think about this question. Think about this question. Why we want to make the baseline larger? Yes, improve the scale, improve the accuracy. As you can imagine something like that. Suppose you have two cameras like this with a very little distance, but you have a point which is 1 meter from the camera. Then which means you will have a very little parallax between which means the angle of the ray from the two cameras, and then this will increase the uncertainty or the error on the depth direction, right? But if we have two cameras with larger baseline, then which means it's still a meter in front of the camera, but the angle we observed is quite larger than before. Then which means we will have a much more accurate estimation of the depth. So that's the main reason, but we can't do that in the stereo. So normally if you can buy a stereo camera, the baseline is around 10 centimeters to 20 centimeters, something like that. It can't be too large. Normally what we use is about 10 to 15, something like this, but not quite large. That's the one problem, which means it is limited by the size, which means it has limited accuracy. And another problem is the two cameras they used, even they're from the same factory or something, then the two cameras are not exactly the same. So which means it sometimes brings some troubles about feature checking or feature extraction or something. All right, and also the synchronization is a big problem. It's a big problem as well. So I have a project, I have experience on that. So I have a project which is doing the lapos. We are trying to build a laparoscopy. A laparoscopy is a scope. It's a scope we use when we do the keyhole surgery in the stomach. Right, so we put the camera into the body and we do the minimally invasive surgery. So we want to build a stereo laparoscope. Then what we use is we try to use two small cameras and we try to like control it in ROS. But the thing is, it's quite hard to make to get the synchronized images. That's the problem. The synchronization is a problem as well. So if you want to use a stereo camera, my suggestion is don't build it by yourself, but instead buy one. Because if you buy a stereo camera, the synchronization is very well adjusted in the hardware. All right, I talked too much on those. So when you have chance to work on those sensors, you have some better feelings on that. So those are some feelings from my experience. All right, so let's move forward. The example 4.
That once 3D object
centimeters.
So so this example I think is similar to what we have before. Right? So it's used sort of like single cameras. It's a lot of multiple cameras, but it's taken in different places. Then we can do the feature extraction, feature meshing, and do this triangulation to get the 3D location of the of each of the points of each of the feature. Then what they did is they called it bundle adjustment. So it's not only from two images. So suppose you have multiple images, you have 10 images, and you want to get the optimal solution of the location of each of the points. So suppose you have 10 images, and from each of the images, you can observe the same point, the same 3D point. And from any of the two images, you can calculate the location of that 3D point, right? But you have 10 images. How can you get the optimal solution of that point? Optimal solution of that point. Then that is called boundary adjustment. You can search on the website. There's a lot of like articles about boundary adjustment. The boundary adjustment means if you have 10 images, observe the same point or observe a lot of points, but they have overlaps between different images, more than two, then you can optimize them together to get the structure of the environment. This is what they used in this case. And also, as you can see, it's not only the 3D location of the points, but also the color. They show the environment in point cloud. We call it point cloud. So which means a set of points, and which if you display it, then you can see the structures, right? And here you can also see the textures as well. Why we can do that is from the point cloud, and by using the cameras, we can give a property of each of the point in a point cloud. And what we always gave is the RGB. Then if you give an RGB for each of the points in a point cloud, then you can show your point cloud in colors, right? And this is much easier when you use RGBD sensors, because it can directly give you the depth of the image, of each pixel in the image, and also from the image you have RGB already. Then it's quite easy to convert it into point cloud with colors, and that is what we always used as the information from the RGBD sensor. All right, and the next one is the visual serving.
information. It also gives you.
Let me come back a little bit. Yeah, sure. So video serving is, we definitely have a lecture about video serving. I think it's a lecture 10 or 11. I think it's 10, lecture 10. So we have video serving. If you are interested in that, so go to lecture 10 and see the video record of about that, right? So as I mentioned before, so the video serving is some kind of like we use camera or vision sensors to help control of the robot. For example, if you close your eye, you don't know, you want to pick up the phone on your on the table, you don't know where is it, right? But you open your eye, you see, oh, that's my phone, and I will take it. It's similar in the, it's quite similar in the video serving. So suppose we want to control the end effector to pick up something. That's the case, right? You want to control the robot arm, the end effector of the robot arm to pick up a ball, but we don't know where the ball is. Then we put the camera on the end effector. We put the camera here on the end effector, and by using the image of the information from the camera, which are the images, then we can adjust my control to pick up the object. So that is video serving. So here, the sensor we use is the camera, and what they want to do is the video serving to control the to use the camera to help the control of the robot to accurately pick up something and do some tasks. All right, and then we have a, so we are going to introduce the principle of video serving later in lecture 10. All right, and here I want to say a little bit more is, if you can see this sensor is called Swiss Ranger. It's called Swiss Ranger. That is the first version, in my mind, it's the first version of the RGBD sensor. So that's an RGBD camera. It can provide you image and also the depth of the image. That's a very early version of it, and it cost a lot, if I remember correctly. So we in our center we bought that. We definitely have that sensor. I think we bought it in 2009 or 2010, I think. And at that time, the price of that is 40 or 50,000 US dollars, something like that, I think. It's pretty expensive, but now you can quite easy to buy a real sensor. Something is a couple of hundreds, right? So which is quite easy. At that time, it's pretty expensive. Yeah, this is just what I want to say. All right, so let's move forward. The example 6. Example 6 is the same. So that is the video serving as well. So if without any control from the vision, so it's quite easy that it can't, the needle cannot reach the target to get the biopsy of that part, right? But what we can do is, if you can see here, the top, the image on the top right, then we can use ultrasound. So the ultrasound can see inside the soft tissue, and also it can provide you the image inside it, which you can see is on the left, right? So it's similar. We can use the ultrasound image as the image input for the video serving, then to adjust at all the time of the needle, the control of the robot of the needle to reach the target. So that is also a video serving, but in the medical case, and we are using the images from the ultrasound instead of a normal camera. All right, so those are the answers from my point of view for the activity 1. And then we also have an activity 2. But I'm thinking not to discuss about that. That is homework. We are going to discuss about this in the next lecture. All right. So this activity is this control robot. As you can see, so we have a fact robot. So we do have this fact robot in our center, and we have some projects about controlling the fact robot. If you choose the fact robot, you have the chance in this semester, I believe, you have the chance to work on a real robot. But before that, you need to test out. Let's talk about it a little bit later. So the robot starts from arbitrary location and come to the table and try to pick up the object on the table. And we are going to answer the questions which are similar to what we had before. Think about that. So those kind of questions are helping you to divide a project into some details. For example, if you have a project about making a indoor robot starting from the charging place to any of the place and pick up something and deliver to the people. You want to suppose you want to do this kind of project in a future carrier, but then what we want to start, right? So you need to think about in this kind of application, how many problems involved in it. You divide it into small problems. Then for each of the problems, you think about what kind of sensor and what kind of like control method we are going to use together to solve each of the problem, right? And then after that, you know how to solve the problem. You know how to finish the project. So this activity tries to let you have a general feeling, a general understanding, and also the thinking about if you have a project, what you are going to do. And I believe you are definitely using that into your group project. All right, so that is what we have for last for the wait a minute. For the last lecture, and then after that we have some introductions of the sensors, and I'm not going to talk too much about that. I believe you watched the video as well. Then there are some classes of sensors, for example, active or passive. So which one is active, which one is passive? You can think about that, right? So watch the video I recorded before, and think about and go through everything on that. And if you have questions, you can come back again at any time. Then after the introduction of the sensors, we mainly want to talk about camera first, because camera is the most commonly used sensor we have in the robotics or mechatronic systems, because it's quite easy to get, it's quite cheap, and also it provides you a very direct information of the environment, right? And it's quite close what we have from our eyes. So the camera is really, really commonly used. And I don't want to introduce all of them. So you need to watch the video about the complete lecture we did in last semester. Then what I want to introduce today is the most important part in the camera, which is, we call it camera geometry, or we call it single wheel geometry, or we call it principle of the camera. Which means, suppose you are going to use the camera, you're going to use the camera. You have an image, right? So if you watch the video, you know the definition of the sensor is it's an input output, and you have a relationship between the input and output, right? So in this camera principle, or we call it camera geometry, so we are talking about the relationship between a 3D point in the environment and its corresponding projected point on the image. In short, for the camera geometry, we want to know if we have a 3D point in the environment, where the point is going to be projected onto the image. We want to know this. So that is the camera geometry. We also call it a camera projection. This is super important, super important, because if you want to use the camera, you need to know the relationship between the object on the image and the real object. Then you can use this relationship in somewhere else, right? So that is super important. If you want to use the camera, you must know this. That's why I want to only introduce camera geometry in the class time. All right. So at the beginning, at first we always suppose the normal camera, it obeys the pinhole model. The pinhole model. Suppose here is the optical center. Then if you have a 3D point here, it will go through this point and project it to there. So that is the pinhole model, right? So it's a straight line from here to here on the image. All right. So that is the pinhole model. So for normal cameras, we always suppose the pinhole model. All right. Remember that. Then based on this pinhole model, that's derived if we have a 3D point. How can we calculate the 2D location on the image? All right. So if we rotate the image from the back of the camera to the front of the camera, something like this, then we have the pinhole model, something like that. So suppose the capital X is the 3D location of the feature of the point on the environment, then the projection onto the image is here, which is small x. Then it is on the line between the camera center and the 3D point. All right. All right. Then let's think about how to calculate the location. So if we only consider the y and z plane of this figure, then we can have something like this. So this figure is the projection of that figure on the YZ direction, right? And in this figure, we know the length between the camera center and the image plane, we call it focal length, right? So that's the focal length. That's the length. That's the distance between the camera center, which is the length, to the image, right? So here, this distance is the focal length. We know that, right? And we know this triangle. Can you wait a minute? I think it's better if I can make a laser dot. All right, cool. So this triangle is similar to this triangle, right? It's similar to this triangle because this angle is the same, right? Then, because they are similar triangles, then what we can do is this distance divided by this distance is equal to this distance divided by this distance. Is that right? Sorry. Right, so again, this distance divided by this distance is the same, is equal to this distance divided by this distance because they are similar triangles and this angle is the same, right? But if we go back, this distance, what is that distance? That distance is the y, coordinate of that 3D point. We know that already, right? And this distance is the z coordinate of the 3D point. We know that as well, right? And this distance is the focal length. Suppose we know the focal length, then which means in this equation, this divided by this is equal to this divided by this. The only thing we didn't know is this distance. That distance is the y coordinate of the 2D point on the image, right? Then which means from this figure, we can calculate the y coordinate of that 2D point on the image, which is this, which is f times y divided by z, right? Then this is the YZ plane. So if we consider the XZ plane, the figure is similar and the equation is similar as well. Then we will have the x coordinate of the 2D point is f times x divided by z. divided by z. All right, then we know the location of that 2D point, on the image, right? This is what we call central projection, but this is not the end of this projection, right? This is not the end of projection. But just let you know, this is called central projection. And if we consider, so if you remember, when you have an image, the origin of that image is not in the center. So here, P, we call it principal point. Principal point is the intersection between the main axis of the camera and the image. As we can see, by using this method, what we got the point is in the coordinate frame, is with the origin of the principal point. But what we always have in the image is we always have an image with the coordinate with the origin on the top left. But here this is a rotated one because in the last figure we rotated it from back to here. But normally we have an image with the origin on the top left, which means we need to move the origin from the principal point to the top left. But if we know the location of the principal point as Px and Py, if we know that point already, then it's quite easy to do. We just need to plus the Px on the x coordinate we calculated and plus Py on the y coordinate we calculated, right? And this is called central projection with principal point offset. This is called the central projection with the principal point offset. All right. By using this, you can calculate the small x, which is the 2D location of the projection on the image in the image coordinate frame. All right. All right, so that is called central projection with principal point offset. All right, but this central projection with principal point offset, you can only apply it when the 3D point is in the camera coordinate frame. So we talk about anything in the camera coordinate frame, right? So we know what is y and what is z. Then which means this 3D point is in the camera coordinate frame. So which means if you have a question in your quiz 1, quiz 2, or final exam, as saying I'm giving you a 3D point. That 3D point is in the camera coordinate frame, and I want you to do this projection to calculate the 2D location, the 2D feature, the 2D location on the image from the projection. And what you can do is you can directly use this central projection with principal point offset. The central projection with the principal point offset. All right, so you can apply the second equation. So you can only apply this if the 3D point is in the camera coordinate frame. If it's not, that's a general case. I'll show you a bit later. All right. So that is central projection with principal point offset. Then I'm also going to introduce you the matrix formulation. It is much easier. It is much easier when you apply it to the encoding and also some other things. This is the matrix formulation of the central projection with principal point offset. So suppose you have x, y, z, which is the 3D location of the 3D point in the camera coordinate frame. Again, in the camera coordinate frame. And what you want to do is you put 1 here to make it a 4x1 vector of the 3D point. We call it a homogeneous presentation of a 3D point. So by saying homogeneous, which means if you have a 3D point, then you have 4 elements. you have a 2D point, you have 3 elements. So that is the homogeneous presentation. So adding 1 here, x, y, z, and adding 1 here. And then you have a camera projection matrix. It's a 3x4 matrix with a first 3x3, which is f focal length, and 1, and principal point x and principal point y. All right. So remember this equation, and when you do the coding, when you do some calculation, and you know to where you are going to put the parameters in. Right. So x, p, x, p, y are the principal point, and f is the focal length. And also you can rewrite this equation to this. And this I means a 3x3 identity matrix. Identity matrix means it's a 3x3 matrix, and you only have elements on the diagonal elements. And for each of the elements on the diagonal is 1. So which means this matrix is a 4x4, it's a 3x4. Let me write something on that. So for this matrix, so K matrix is here. It's a 3x3, and this X camera is this. And what is this? It's a 3x4 matrix, which is 1, 0, 0, 0, 1, 0. Sorry about my writing, and 0, 0, 1, and 0, 0, 0. That's a 3x4 matrix, right? And why we are writing this is because we can get this K matrix out, and you can see this 3x3 K matrix. It only contains the focal length and the principal point, right? We called the focal length and the principal point as the camera intrinsic parameters, because when you have a fixed camera lens, a fixed camera already, those parameters are fixed. Because it's the only difference because of the manufacturing, right? So when you have a camera, it's a fixed lens, then those parameters are fixed already. Then which means before you use the camera, you can do a calibration. So later in the hand activities in the tutorial, Marlene will show you how to do this calibration. So there are calibration toolbox. Then you can use the camera to take some images from checkboard. Then you can calculate those parameters. And after you do this calibration, you can use it later in your later applications as the node thing. So as the constant variables. I mean constant values. Theoretically, the numbers are not changed, which means if you can do the calibration once, you can use the parameters forever. But in the real applications, in our experiences, those calibration parameters will change during the time. For example, I use a lot of cameras. I did hundreds of thousands of calibrations already. But for a same camera, for each time I do the calibration, the numbers are different, but not that different, but they are different. So if you want to do some, in your future career, if you want to do some accurate control or something, if you want to use the information from the camera quite accurate, then it is better when you do the application, do another calibration before that. But ideally or theoretically, you don't have to change that, because theoretically it doesn't change. But in the real case, it's better to do the recalibration before you're applying for that. All right, so that is the camera intrinsic parameters or camera calibration parameters, and that is the camera calibration matrix or intrinsic matrix. And later, Marlene will show you how to get the focal length and principal point from the camera calibration. That is quite important as well. Again, that is quite important as well. All right, so this is the central projection with a principal point offset, but with a matrix format. And I forgot to introduce is, this is a 4x1 vector, and this is a 3x4 matrix. And after that, you will get a 3x1 vector, 3x1 vector. That is the homogeneous presentation of a 2D point. And it's quite easy. If you want to convert it into normal 2D point, we call it UV. You just use the first element divided by the last one. That's your X or your U. And the second element divided by the last one, that is your Y or V. Right? So when you want to convert the normal 3D point or 2D point to the homogeneous point, you just add 1 at last. You just add 1 at last. But if you want to convert the homogeneous point into normal 2D or 3D point, you use the first 2 or 3 elements divided by the last one, then you have it. All right, and that's your homework. And think about why we need to divide that, because we're adding 1 here. So we delayed that one is fine, but we can't do that. Why is that? And why we want to use this homogeneous presentation. Think about that, and we'll talk about it in the next lecture. All right, and then let's go to the normal case. So normally you can't get a 3D point in the camera corner frame because your camera moves, right? The camera moves, and the 3D point, the 3D world, it doesn't move, suppose. Then when the camera moves, you can't get the 3D point in the camera corner frame. But what we normally do is we have a 3D point in the, we call it the global corner frame or world corner frame. And we want to project that point onto the camera, right? And what we can do is, it's quite simple. You know the central projection with the principal point offset already, which means if you have a 3D point in the camera corner frame, then you know how to do this projection, right? But if you have a point in the world corner frame, but it's not in the camera corner frame, how can we do? It's quite easy. If you have a camera pose, if you have the pose of the camera, you can transform that point in the world corner frame into the camera corner frame. Then you can apply for the central projection with the principal point offset, right? So here the R is the 3D rotation matrix, 3x3 rotation matrix, and T is the 3x1 translation vector. So if we have the R and T, which means if we have the rotation translation, which means if we have the pose of the camera, then we can transform the 3D point in the world corner frame to the camera corner frame. Then we can do the central projection with the principal point offset, as what we did before, right? And this is what we did. So we have, this is the central projection with principal point offset. Suppose we're having the 3D point in the camera corner frame, right? But if we don't have, it's quite easy thing is we can do the coordinate transformation first. So this is the coordinate transformation matrix, which is the 4x4. And this is the point, the 3D point in the global corner frame, which is 4x1. It's homogeneous as well, right? Which is 4x1. Then which means if we have the pose of the camera and also we have a 3D point in the world corner frame, the first thing is we can do this transformation. We can do this coordinate transformation to transform this point from the global corner frame to the camera corner frame. Then we can apply the same thing. Right? Then this is the camera projection model. That is the general one, the general camera projection model. So suppose a 3D point in the world corner frame, then what corner frame? Then what's the projection of that 3D point? All right. Then we can rewrite that equation into this. This is a 4x1, 3x4, 3x3, and 3x3, right? And this R and C, this C is the T, which C means camera center. C means the camera center, which is the translation of the camera pose as well. That's the same. And this is 3x4, and this 3x3, and this 3x3. All right. Then think about, this is a general case. Think about the 3D point is in the camera corner frame. It's not in the global corner frame. And which means this rotation, there's no rotation, right? So rotation matrix is identity, which means we can delete that. And for translation, all the camera center is 0, 0, 0. So we can replace C as 0. Then if we're doing this, this is exactly the same as the formulation of the central projection with the principal offset, right? So this is the general case. And then you can also apply it to the central projection with the principal offset. All right. So this is the camera projection. This is the camera projection, and this is super important. Do remember this is super important because if you want to use the camera, that's the principle, and you need to know the relationship between real world and the image, and that is the principle. All right. And sometimes we rewrite this equation by this. And the P matrix, which is this, we call it the camera projection matrix, which is the P matrix is 3x4. This is what we talked about. All right, so those are the principles of the camera projections, and we do have an activity. So try to do this activity by yourself. And you can write, you can do the calculation by using hand, or you can write a code. You can write a code about that as well. All right, and do try to practice on that by yourself, and make sure you know how to do this projection. Do make sure you know how to do this projection. All right, so try to write down equations and try to write the code. And I do suggest you try to write the code by both this normal equation and also the matrix equation as well. Try to practice on solving the activity by yourself on that. And later in the tutorial, then as Marlene will show you how to do this calibration. So which means we only need to print this checkbox and use the camera to have multiple images on the checkbox. Then use the images, you can calculate the focal length and principal point, and also distortion parameters as well. All right. All right. Okay, so that's mainly all for today's lecture. And we have 5 minutes left. Let me talk about the quiz 1 in next week first, and then if you still have some questions, you can directly unmute yourself and ask. All right. So for the for next week, at the beginning, at the same time for the lecture, for the class, at the beginning we are going to have our quiz 1. So it is in class quiz 1. So please do join this Zoom meeting. All right. And during it's mainly about 40 or 45 minutes for the quiz 1. So it's in class. So at the beginning of the class, we are going to have the quiz 1. So we will release the question during the Zoom, and also the questions may include short written answers, calculations, and the computer experiments. All right. So it will include everything you have from lecture 1 until now. Not until now, until the end of this this class, which means it will also include the things you have in the tutorial later when Marlene shows you. All right. It can include everything. It's only 5%. It can include everything. And since it is possible, it may be to have some computer experiments as well. So do make sure you have your computer ready. It may include everything you have in the 2 lectures and 2 tutorials. So make sure you you make sure your laptop, your computer is ready for the tutorials, for which can function for the tutorials. If you can't, you may be in trouble if you have the question, have the questions about computer experiments. All right, for example, like MATLAB, ROS or something, right, or Linux or something. All right, and I think I have some questions. Now the submission of quiz 1 is a report. I'm not asking you to show me something because time is quite short. I can't see the demos one by one. So there will be a report for you to submit. All right. So no multiple choices. There will be short written answers or calculations or the experiments or combination of them, something like that. No multiple choices. But you need to write a report on that. So you can write it by hand and take a picture and upload it on UTS Online. All right, or you can write it in a Word document and submit it on UTS Online, something like that. Or you can convert it into PDF and submit it. Right, so everything's fine. So everything as your convenience. I try to write a report and submit it to UTS Online for quiz 1. And because for quiz 1 it only contains the things within the two lectures and tutorials. So we don't have a practice quiz. Sorry about that. We don't have the practice quiz, and it only has 5%. But 5% is still 5%, right? So try to get as higher marks as you can. All right, so any questions about the quiz? Any other questions about the quiz? You can ask questions in the chat, or you can unmute yourself to ask. Both are fine. Yes, you have. So for all the Robotics Studio 1 students, you need to do the quiz 1 and quiz 2. All right, you have to do the quiz 1. All right, so please join us. Okay, that's a good question. So I do suggest do not submit any MATLAB code. All right, do not submit any MATLAB code. So if there is a calculation, try to write the equation there and try to use MATLAB to help you on the calculation, and then put the number there. I do want to see the process when you solve the problem. Suppose you have a calculation. What I want to see are both. One is the process, and the other is the result. All right. So I do suggest not submitting any MATLAB code. Yep. Yes, you need to submit things online. So you need to write a report and submit online before the deadline we have. So suppose we have 40 or 45 minutes. Then after you finish that, you have 5 minutes to upload your report to the UTS Online. All right. So suppose in the next lecture at the beginning at 12, so we start the I release the question, and you start doing your quiz 1. And after 40 minutes, as I stop, and then you have 5 minutes to upload your report to the UTS Online. And then after that 5 minutes, the system will close. Is that clear? I can't say too much about the quiz, but what I want to say is it will include everything in the first 2 classes, including the lectures and also including the tutorials. And also, please review the video record, because in this matter I didn't mention everything about the lecture, because I suppose you you viewed the video record already prior to this lecture. I can't say too much things because it's only like 2 classes, right? So everything is there already. You more or less know what we have already. All right, and you don't have to repeat the question or in the report. So which means if you want to write a report, you just say this is question 1 and you answer, and that's totally fine. Because because it's 5%, there must be 2. There can't be too many questions, and I know each of the questions. All right. Any other questions? It's open book. It's fully open book. Previously, it's not. If we take the lectures face to face in the computer lab, previously it's not. It's not open book, but now it's open book because you're doing it online, so it's open. It's totally open book. Yeah. But the thing is, I want to mention is you only have 40 minutes. Then time may not be enough if you spend too much time to find your answer. Just try to practice on everything you have on the first two classes. No, this is what I mean. So don't do a screenshot or don't try to copy the copy the code onto it. I can't say too much at the moment, but the thing is, if there's a computer experiment, it's definitely you can do some screenshots and copy the results from what you have from the computer to the report and write it. And also you can get some maybe figures or something you want to write in the report. That's totally fine. So for computer experiments, it's totally fine. But for the calculations, if you want to show, if there's a calculation and you want to show the process, it's better to write the necessary equation there, and then use the computer to calculate the answers and write the answers there as well. Right? Instead of like directly screenshot what you have on the code to the report. Example, I think the report is quite straightforward. It's quite straightforward. So don't worry too much about the report. But what I want to, when you have the questions, I will detail about what is required to write into the report. All right. So don't worry too much about that. It's quite straightforward. 5%. It's quite straightforward about what you want and what you write into the report. The report is not the same as the report for a group project. It's different. It's just the report is just about the answers, and I'll let you know what kind of thing I need you to put in the report. Okay, so I can't say if there is a calculation or not, but it's possible to have calculations. It's possible to have calculations, and what you're going to do, as I mentioned before, what you're going to do is you write the numbers and the equations onto the paper or onto the MATLAB, onto the Word document or write it on the paper. Then you can use MATLAB to do the calculation and put the answer on it, something like that. All right. All good. All right. I think time is right. What is that? Do we need to show working out? You need to write the necessary equations and try to do the calculation from MATLAB or something else, and then put the answer in it. Just this kind of thing. I want to see the necessary equations you have, and what numbers you're putting it into it, something like that. Then the calculation is quite easy, right? It's open book. All right, so if everything's good, Then I will finish this lecture. And if you still have questions, about this lecture, and we can try to, you can send me email, or you can try to ask Malin as well, or you can send email to me. All right, or something else we can talk about in the next lecture as well. All right. Okay, so thank you very much for joining us today for the lecture, and let's move to Malin for the hand activities and tutorials. Thank you very much. Thank you.
Thanks, Ian.